but I'm very, very grateful and happy to be introducing Shravan Narayan, who is an assistant professor at UT Austin, who flew with less than a day's notice here to give this talk. So a big hand to Shravan.
Okay.
And please take it away. I see your screen is not displaying yet.
Perfect. There we go. Awesome. All right, so hello everyone. I'm Shravan. I'm subbing in. Oh, I should be here. Hello everyone. I'm Shravan. I'm subbing in for Dayan today. I should kind of start by saying a lot of the stuff I'm going to talk about is the collaborative work of a ton of people. I'm just here telling you about it. And I know a bunch of people in the room might have wanted to hear from Dayan, but no worries. I'm well set up to fill you in on all the stuff that we've been up to as a group. And in fact, I started these slides 7:30 p.m. yesterday, which is a full 12 hours before Dayan would have started the same talk. So we should be fine. We should be fine. So I actually have met a few of you in this room. For those who I haven't, let me just tell you very quickly who I am. I'm an assistant professor at UT Austin. I actually did my PhD at UC San Diego working with Dayan. And the stuff I'm going to tell you about is research that I've been kind of involved in for the last 8 years at this point, which feels like quite a while. And I'm going to start this talk at the beginning, just so that I'm kind of making sure everyone follows along. I know a couple of you may have seen versions of this talk. So what I'm going to do is also explicitly mention all the new stuff I put in when that comes up. So feel free to let your mind wander if you've seen some of the bits before. OK, so let's start at the top. Why are we worried about, or what are our interests with WebAssembly, right? And so it starts with something that looks like this, which is software suddenly realizing, oh, there's a 0-day in the wild, we need to go patch this. And this happens with browsers, for example, all the time. And these are not simple bugs. They are sophisticated attack campaigns with like a chain of bugs starting with memory safety, privilege escalation, platform-specific stuff, and so on. Now, if you zoom into just the core bug in this big attack campaign, you're going to actually see that it's a CVE in this library called FreeType, which is a font rendering library used by Chrome. Not written by Google, but used by them. So it is a third-party library. And this actually means that Chrome had a 0-day because of code they didn't even write. And this sort of thing is super common. It happens again and again. And don't take that 2020 example like as the only case of that. I can literally give you one from last month if you want. Right? And these sort of memory safety bugs simply aren't going to go away no matter how much we wish for it. 70% of all memory safety bugs or like long-term studies in browsers and OS are these sort of, 70% of bugs are these memory safety bugs. And now the obvious way we would like to tackle this is to, start doing things a little safer, maybe rewrite things in Rust. Now, as a practical matter, there's a lot of code out there, a lot of C, a lot of C++. It's hard to rewrite that overnight. It's hard to rewrite that over the next decade. It's hard to rewrite that over the next few decades, if I'm honest. The other thing we can kind of do is to split apart all our applications into privilege-separated kind of designs, which is make them a bunch of processes, separate out the code, and that way each process can't affect each other. Now, browsers are doing this pretty extensively already, and we're hitting a ceiling when it comes to performance of that style of doing things. And all of this is like discussed in detail in various talks given by a lot of folks, actually. So when we looked at this, we wanted a different way to tackle this, and so we started with this thing called in-process sandboxing, which in short was, let's take all the third-party libraries or even first-party libraries in Firefox and start putting them in WebAssembly sandboxes. So we're no longer wanting to build an application like a monolith where a memory safety bug in one component affects the world. Let's kind of keep things contained. And so, and we did actually. It did actually happen. It took quite a while. So I'm going to start by telling you how we actually made all of that happen. And here's roughly what I'm going to try to cover in this talk. We'll start with talking a little bit about how we made WebAssembly workable for this library isolation kind of use case. And I'll talk about all the stuff we've been doing over this, I want to say, 6-7 year project, including stuff that's just happened last week. After that, we'll talk a little bit about the security of WebAssembly and sort of work we've been involved in. Chris has actually talked to you about that extensively, so I'm not going to spend a lot of time on it. I just want to kind of show you how it all fits into the overall picture. And finally, we're going to talk about performance. We're going to talk about performance a lot, actually. So we're going to tell you about 3 different ideas we've had to speed up WebAssembly. And then, if time permits, and I really hope it does, that's the cool stuff at the bottom, the ongoing work that literally no one has seen. It's on my computer and nowhere else. Okay. All right, so let's just jump right in. Start with process sandboxing. All right, in an ideal world, I would just be able to do this. I take Firefox, compile the libraries to WebAssembly, and I'm done. And this is my little approximation of a WebAssembly compiler, which is to insert bounce checks before every memory access. We all know it's a little more complicated than that, but that's good enough for now. Now, if I could just recompile these libraries and then use it, that should kind of be enough, hopefully. In reality, that's not quite the case. Because when you do this, firstly, you need to figure out how to really decouple the library. Not just move the code out, but deal with all the shared data structures. And then you need to restart sharing just the data structures that make sense to share, that are actually used by both the host and the library. And you might not want to copy data too aggressively back and forth, or you'll wreck your performance. And what's more, you have to insert a bunch of security checks, because the library could corrupt the data structure and you could end up using it. So if you don't check it, all of the security you get from WebAssembly is gone in this use case. So by the time you actually do this, it becomes quite tedious. So let me show you a super simple example. This is the code for an application that renders JPEG images. It's super tiny. I've tried to fit it into one slide as possible. Don't worry about reading it, right? Like it's an application that renders JPEGs. If I were to make all of those changes I just showed you on the last slide to actually integrate a Wasm sandbox libjpeg in an application, that's what the code looks like. Again, don't read so much into it. Just, for example, look at the middle line. Just look at the number of checks and ABI conversions and marshalling that has to happen. I don't know what that line says anymore, and I wrote it. So this is clearly not going to work in practice. And even if you somehow succeed in doing this for one library, that's an incomplete picture of the libraries in a browser, of the third-party libraries in a browser. I think the actual image extends about 3 times the size of this projection screen. So we're not going to get away by doing this slowly. And we're not the only ones to kind of come to this conclusion. There are other folks as well, folks at Google who've tried this. And the conclusion is it's pretty much impossible to do this by hand. There's just too much interleaving. There's just too many changes required. So this is where we started this work called RLBox. It's a work we published at Usenix Security 2020. And the idea was to use a type-based approach to sandboxing, where types can hide all of this mess. We can hide the low-level sandboxing details, deal with the ABI conversions automatically. And by API conversions, I think this room probably knows what I mean. WebAssembly, at least the memory 32, uses more or less 32-bit ABI conventions, 32-bit ints, 32-bit longs, so on. That may not be the same as your host. So you suddenly have to deal with all of that, and RLBox will do this for you automatically. It deals with data marshalling as much as it can automatically. It uses types to track untrusted data and control flow, and essentially give you kind of compile time errors if you didn't add a sanitizer to data that you should have sanitized. It also allows you to adopt these sort of security checks and make all those changes I showed you incrementally. You can literally do it line by line. You can change one line, compile the whole application, see that every test passes it, and deploy it. And in fact, when we did this in practice, we did do partial migrations and in fact deployed it. This did actually happen in production. And all of this is done with RLBox as a pure C++ library, which was the hardest part of this. And really, if you look at RLBox in its core, it just boils down to 3 principles, which is RLBox wants to be in charge of control flow in and out of the sandbox. So when you invoke a function in the sandbox, use its API, sandbox invoke. Next, every time you get any data from the sandbox, you should mark it as tainted. So in this example, when you read the size of an image parsed by the libjpeg, you've obviously got that from the sandbox libjpeg. So that is now a tainted uint32, not a uint32. And finally, when you use this tainted data in functions like memcopy, RLBox is going to force you to add a sanitizer there. Now, I should clarify, it can't tell you whether the sanitizer is right, but it's going to tell you you need to have something here. Okay? So hopefully we're all following so far. And I just want to show you the same libjpeg application example and what it looks like with RLBox and these 3 rules. So this is what it now looks like. There is a lot of yellow, but if you actually look at it, it's far more readable. It more or less, the original code stays as is with a little bit of type annotations here and there. And this is kind of the thing that actually makes things practical for us. And why all this matters is when we had this sort of framework to help with our library sandboxing, we could sandbox a library in a matter of days. Now, if you include testing and all of the things involved in real production deployments, let's call it a couple of weeks. Still very reasonable. And so we actually used this technique and deployed this in Firefox. And this was actually a very, very detailed and slow process, just because anything that touches production for millions of users, people want to be careful. So we actually did this research in 2018, 2019, tried a bunch of approaches to make this work. It didn't work. Finally, we decided to work with Lucet, which is, I want to say, a precursor to Wasm time. I don't know if that's the technically correct description, but it's a Wasm compiler. I think right now it's no longer supported and everyone uses Wasm time. But we started here and we got this working in Mac and Linux for a single library, just one, sandboxed in Firefox, and it's running. And it took us the better part of 2 years to actually get more than this. And one of the key elements we had for our use case that was successful for us is moving to a different WebAssembly compiler, Wasm to C. And I'll talk a little bit about this. In this use case, it actually turns to work out pretty well. And with this move to Wasm to C, we were actually able to get every operating system that Firefox will run on supported. So this includes Linux, Mac, Windows, and Android. So literally on the phones. And we sandboxed a whole bunch of libraries, and this has all been running since then. And after that, we spent a bunch of time improving all of the infrastructure to kind of keep this all working well in place. And this has nothing to do with sandboxing, but just shows you a little of the extra pieces that are involved in making all this kind of work out in production, right? Like things like crash reporting, how quickly do you spin up sandboxes, when do you destruct them, how do you kind of keep things in sync with upstream code, et cetera? Because we forked Wasm to C for the longest time, and it was a bit of work to get all that merged back upstream. And something that happened in September 2023 is we started looking at a library that relied on SIMD. And WebAssembly SIMD is now well supported, which is great. We are a very, very grateful user of this feature. But we needed to get it to work in Wasm to C. And for those of you who don't know, Wasm to C is this interesting compiler that takes a WebAssembly file and converts it back to C. Not the original C that you started with, but C with, let's say, bounce checks, just for simplicity. So it's sandbox C. And effectively, when you think about it, Wasm to C plus GCC is a Wasm compiler, if you just put it in a box. And we needed to figure out how to support SIMD here. And the way we did this is to use this library called SIMD everywhere, which basically converts intrinsics to intrinsics. And so if you actually look at the round trip path of how we are compiling code now, it's to take a library which uses intrinsics, libpng for example, convert that to WebAssembly and use Wasm to C to, and Wasm to C SIMD support itself uses SIMD to convert the native intrinsics to Wasm intrinsics. Then we, I messed that up. Let me try that again. We take the libjpeg code, compiling with Clang to a Wasm file, using SIMD everywhere to convert the native written intrinsics into Wasm SIMD intrinsics. We take that file, compile it with Wasm to C, use SIMD everywhere again to convert the Wasm SIMD intrinsics to the native intrinsics, and compile this. And weirdly, this is all fast, or fast enough. Like it had no reason to be fast. It just was fast enough, and we shipped it. That performance of that library was 30% overhead or 40% overhead before, and I think it was down to 7% after that. And stuff that we've been doing since then, we've been trying to improve the RLBox framework. We have something called RLBox V2 in the works, and I'll show you just a couple of the problems it handles. And this other project that's ongoing, which I literally had to name this morning for this slide, which I'm going to call Sandbox Auto Sanitizer. So this is some of the new stuff, and I'm going to talk a little bit about that in a couple of slides. But first, let me tell you about all the stuff that's happened up to now. And there's going to be an obvious question when you look at this sort of timeline. Why so long? Well, cross-platform support is just painful. It is. And by the time you hit all the OSs, all the architectures, and we support more CPU architectures than that, by the way, we support all of them, and all the compilers, this is a mess. So for example, here's my description of one of the bugs I had to deal with. When using MinGW on the build servers in some OS, I don't remember what it was, thread local global variables of struct types failed to compile because of, and at this point, if your head hasn't exploded, I worry for you. This is painful. On the other hand, for those of you who are following all of that and are like, oh yeah, I handle these bugs all day, please talk to me after. You sound like my next collaborator. All right. Beyond that, we had to work a lot to get Wasm to see, fast, building efficiently, and so on. There's a bunch of fixes I won't talk about. But at the end of this is what we managed, which is 7% on XML parsing, 10% on font decompression for sandboxing these libraries in Firefox. The XML parsing is particularly interesting because that is a super hard path thing. And that is something that was really, really considered carefully before we sandboxed it because Mozilla was wary that we would kind of destroy the performance. Because everything from SVG files and XML files on the internet are, go through that library. So this was kind of a big deal for us. And the thing that kind of made all this possible was Wasm2C. Wasm2C, and I kind of described the pipeline a bit earlier, but essentially what makes it useful for us is it's super simple to extend. So we can support extensions, in fact, support extra different ways to enforce things instead of just guard pages or just bounce checks, etc. And I'll talk a little bit about this later. We can even do interesting things like ensure the Wasm2C outputted code works with ASAN. Very little work, actually. The only thing we kind of really need to add in is a little bit of like WASI support. We don't want to add all of WASI. Firefox doesn't need it. And we want to keep the TCP low. So we have a very minimum WASI that supports all of this. And literally all it lets you do is print or something and get the time, I think. And the nice bit is that C produced is now compiled with Clang and GCC, which is a compiler that's been optimized for decades. It's great. Like we get good performance out of that. And so here's my kind of controversial question for you, or I don't know, just the interesting question, let's say. What is the fastest Wasm compiler now? And yeah, no, generally shout it out.
Wasm2C plus GCC.
Wasm2C plus GCC. Okay, I might have primed you badly here, which is my fault. Any other suggestions? Wasm2C plus LLVM. Oh my God, okay. Really no mentions of Wasm time. Huh. Well, no, so here's the thing. Wasm time 2 years ago was a slightly slower compiler because it was in development. Wasm time is pretty damn fast right now. It is actually faster than these things. Like despite half the things I tell you, it is still the fastest out there. With a caveat. The thing about Wasm2C code that you spit out is that little bracket at the end. We get to do LTO, we get to do PGO, we get static linking in Firefox. That is another 15% in performance. So no matter how much work we put into the Wasm compiler, sometimes things like that just tend to matter more. So this is an interesting observation for us. And anyway, kind of stepping back, what does this all mean? Well, if we look at the history of bugs in expat, that XML library I told you about, there's a lot of CVEs, a lot of memory safety bugs. And hopefully the goal is we don't have to worry about those anymore. And we had the opportunity to figure this out in practice. So this is a bug, I hope you can read that. This is a bug thread in Bugzilla Firefox. I'll read it out if you can't see it. Essentially, the first question is, let me do this way. Lately, some expat CVEs popped up. The expat library is sandboxed in Firefox as a version 96 with RLBox. But the ESR, the extended service release, it doesn't seem to be covered. Can you investigate whether these vulnerabilities are relevant? Response from Bobby Holly, who's now the CTO of Firefox. Oh, actually, looks like there's a lot of CVE, I'll paraphrase, there's a lot of CVE patches. It's just easier to uplift all of the RLBox sandboxing work for sandboxing expat, rather than the individual CVE patches. So that actually is what ended up happening. And which is kind of this very weird takeaway, which is apparently sometimes like it's cheaper to kind of like even just sandbox it than to sit and fix all the memory safety bugs you have in your libraries. And so hopefully the point of all this was to ensure the CVEs in third-party libraries do not translate to CVEs in Firefox, and we certainly saw an example of that in the last slide, at least for the non-ASR Firefox. And just the engineering-wise, the reason why people seem to care a lot about this is they like their battle-tested C code, buggy bugs and all, right? And it's painful to sometimes rewrite everything. I would rewrite as much code as I can in Rust as long as memory safety was my targeted, like kind of the thing I'm trying to fix. But in scenarios where that's not possible, this is a pretty good way to go about doing things. And the upside is when you do this, you do not have a 4 a.m. O day that you need to get up and go and fix. And so that's kind of where things were as of 3-4 years ago. So I'm just going to give you a very quick kind of thing of the new stuff we're up to, stuff that you may not have seen in previous talks. Okay, what is it that we're doing with RLBox right now? I mean, clearly all of this at least kind of sort of works. Well, the first problem that we are running into in Firefox is sandboxing on 32-bit CPUs is super painful. And yes, Firefox does still support 32-bit CPUs. 32-bit x86 is supported. And, you know, we have a bunch of smart people here. We can guess what the problem might be. 32-bit Wasm does not have guard page support. It has only bounce checks. The takeaway is Wasm running on 32-bit platforms is slow. Turns out that's not the problem at all, because apparently in the real world, it's okay for the software running on 32-bit CPUs to be a little slower. We want it to run, but if it's a little slower, that's okay. And so, and don't get disheartened by this. I'm going to show you how we can fix this even on those platforms, like right at the end of the talk, how we can even target those sort of problems. But it just turned out not to be the biggest thing. And instead, the thing that we had to reckon with is that when using WebAssembly in this context, the linear memory of WebAssembly, we cannot move it. Because WebAssembly obviously refers to all of its memory with offsets, which is great. You can move it, grow it, whatever. Firefox is going to talk about the same memory that WebAssembly is using with global pointers. And once it takes a global pointer to something, you cannot move it. At least you cannot move it easily. Which means the only way we can deal with this is to basically pre-allocate as much virtual space as we possibly could use, and then grow into it as we need. Not at all a problem with 64-bit CPUs. We have tons of virtual memory space. Huge problem on 32-bit CPUs. We have to guess what our maximum virtual memory footprint would be, and literally I have code that calculates, the font file size is 8 MB. I typically see a 3x bloat. All right, let's guess how much max memory we need, etc. So this is a little painful, to say the least. So what we've kind of started doing is asking RLBox to deal with this. And I'm just going to give you the intuition because the details are very involved. But if we can get RLBox to return smart pointer-like things into the Wasm heap, we suddenly can deal with the fact that the heap might move, right? Because the smart pointer can keep looking up, oh, the heap is here now, the heap is here now. So on every access, it just adjusts to wherever the heap is. Now, this is all easier said than done. This could wreck performance, but we are seeing some positive signs on how to make all this work out well. So a second problem that we have to tackle is something I kind of glossed over very quickly, which is, if you remember, I said one of the 3 RLBox rules, sanitize the tainted data before it's used. This is kind of manual. And the story we had for everyone in 2020 is, oh yeah, the sanitizers are simple. Don't worry about it. It's 3 lines on average. It should be fine. We knew it wasn't enough. Everyone knew it wasn't enough, but this was the best answer we could give you. And not surprisingly, we got it wrong once. And there is a bug thread, and the person did receive a bug bounty because all of this code is bug bountied being a part of Firefox. And so we started this work, which is, I'm just going to call sandbox auto sanitizer, which infers or checks the RL box sanitizers using programming language techniques. And the way to make this practical is actually kind of tricky and detailed. I'll talk to you offline about it. But there's actually some very interesting details on how to, actually make this work. And kind of like the proof in the pudding is it found another bug when we ran it. So we got apparently 2 sanitizers wrong. Now, I'm not going to tell you who in the group got the sanitizers wrong, especially when they're away and ill, but, Okay, so, all right, so that should kind of give you a little bit of taste of like all the stuff we're doing just to kind of use WebAssembly for library sandboxing. Now, one of the other things our group kind of broadly has been involved, including with Chris, is how do you use verification and other tools to ensure the security of WebAssembly? And the thing to keep in mind when you use WebAssembly is it gives you memory isolation if your compiler doesn't have bugs, if your runtime doesn't have bugs, that is to say WASI doesn't have bugs, and you're not worried about Spectre. These are the 3 caveats. And this is a fantastic attacker model for web browser security or application library security in general. Oh, I have an extra slide, sorry. But in another use case of WebAssembly, which is the function of a service platforms, this changes completely. So for those not familiar, the way WebAssembly is used in function as a service platforms is clients submit their code as WebAssembly modules, and they're all run in a single process in the server. And that's actually very, very efficient because once you don't have a billion processes floating around, your server is super efficient. This model, however, is quite a bit different. Attackers in this world submit and run their own code, which makes things like Spectre a lot more, worrisome. So what we need is end-to-end security guarantees. And, how do we actually go about doing this? So, sorry, I think I messed up my, there we go, slides, there we go. So what we really want is to preserve Wasm's memory isolation at the binary level when it's running syscalls and when it's executing speculatively. Now, at the binary level, we were involved in this work called Wasm, which that has been taken a lot further by Chris, and I think he might have mentioned some of that in the talk, so I'm not going to dwell on this. The short version is you can look at a binary produced by a WebAssembly compiler and ensure that all of the checks are in place. Turns out WebAssembly has just enough structure to make that actually feasible. And if not, you can always get a little help from your compiler with a little bit of hints. The other thing to keep in mind is we need to, and yes, this is work that is in NDSS 21, if you want to read more details. We also have to pay attention to the runtime. We need to ensure the runtime is safe as well. And the problem being, if the runtime calls the OS with essentially bad parameters, and the OS clobbers the memory that WebAssembly shouldn't have been able to access in the first place, what are you actually getting with WebAssembly, right? And the problem is, the POSIX spec is super complicated. How do you actually deal with ensuring you don't mess that up? And the one-line intuition of why we can kind of actually make verification practical there is it turns out you only have to pay attention to the part of the POSIX semantics that affects the WebAssembly memory isolation properties, which is a far tinier fraction of it. And so if you actually look at the code that implements this verified WASI kind of implementation, it's fairly reasonable. The asserts on top are not that complex, at least compared to other formally verified code that I've seen. So with this, and yes, this is work in IEEE S&P 23 if you want to read more details. And finally, let me talk about speculative safety. And the basic problem here is WebAssembly's security checks. I'm just going to say bounce checks, but security checks in general. It could be CFI checks, memory checks, whatever. They're all at the function granularity. So the moment you have speculative control flow, things could get bypassed. So we've come up with this construct called linear blocks, which basically says don't let control flow get between the security check and the operation that you're securing. So simple example on the slide. If you can't read it, what it says is, oh, look, I'm checking an index to ensure it's in range. I'm making a function call somewhere else, and then I'm loading from that location I just checked. Entirely reasonable code to run normally. Speculatively, funny things can happen the moment you have control flow, that call instruction. So the basic idea is, let's not allow the memory bounce check to be lifted that far up. Let's keep it closer to the use. As long as there's no control flow in between, that's fine. Additionally, when you check the index, we want to use speculation-safe checks, things like masks. And that's the high-level idea. This is one of the most technical and nitty-gritty kind of papers we've written, this Usenix Security 21. But it really boils down to a couple of core techniques and using them well, and this is one of them. There's another thing in that paper which, in hindsight, I might have mislabeled by calling it the register interlock. It's actually what it is a Spectre-safe WebAssembly CFI. Meaning you can actually deploy the CFI and get the CFI properties you want, even speculatively. And talk to me afterwards if you want me to kind of walk you through how that happens, but it's actually kind of cool. And here's the other new bit, which is kind of the follow-up thoughts on this paper, which I've never actually, said out loud. But I think we actually kind of made a mistake positioning that paper, just because we focused on perfection, which meant the techniques cost all the way up to 200% overhead, which is great. We have a way to solve Spectre. That's not a great way, though. So what about an imperfect solution? The thing that I kind of realized in the few years after that paper is there is an imperfect scheme hiding in that paper that costs about 1 to 3% overhead that makes some to a lot of Spectre variants impossible and other Spectre variants much harder. So I really think we should think about deploying some of these sort of things in real compilers, especially in cases where people care about Spectre. We don't have to have them on by default, just in the cases where people care about it. So that is this kind of very brief overview of security. How are we on time?
We're good, actually. I should just be around to give you your 5 minutes. So I've done that.
Okay, it's 5? Okay, perfect. All right, so then let me get through this last bit very quickly because I want to get to part 4. So the last thing we've kind of spent a lot of time on is how do you make WebAssembly faster and more scalable. And there's 3 different techniques I'll very quickly tell you about. And the motivation here is WebAssembly isolation works, but there are some costs. Whether you're using bounce checks or guard pages, there are some performance overheads. If you want Spectre safety, it's even worse. And hardware can help with all of this. And let me just show you just a couple of ways how we can go about doing this. So the first thing I'm going to tell you is this technique we've just dubbed Segue, and it's actually just been accepted into ASPLOS 2025. And the gist is, let's go back to x86 segmentation for WebAssembly. Now, the one-line description of x86 segmentation is it lets you describe the base of a region of memory and the bound of a region of memory. And every time you access that memory with a segment register, like GS, you get a bounce check along with a base add, which sounds a lot like WebAssembly to me. You are essentially getting an operation that is access linear memory with all of the right semantics. The problem, segmentation basically went away for x86 64. This is all the top bit is all for 32-bit CPUs only. And the part they removed was the bounce check, which is a rather important part of WebAssembly semantics. But one of the things we played with is, well, let's just see what happens when we use the remaining part of x86 segmentation, the 64-bit segmentation, which is just the base addition. And it turns out this actually unlocks a whole bunch of low-level compiler instruction encodings and optimizations and cache impact of code sizes, etc. And when we actually tested this on real code, we found that in some cases it eliminated 75% of the overhead of WebAssembly. That XML parsing case, the hot path that we were talking about, 68% of the overhead goes away with this use of segmentation registers, which is wild. We did a workshop paper on this 3 years ago, and that we said 13%, and we were proud of that. And then we ran into this. So it is kind of an interesting point that this is where a lot of the overheads lie. And just to kind of give you a very quick intuition, the reason for that is there is a large drop in binary size. I don't know if you can read that. The median binary size drops by about 6%. So Segue is now supported by WAMR, Wasm'25, and just last week, Firefox started using it for Linux as well. There's another technique called color guard that actually reduces the amount of guard pages we have to use. And there's a lot of the insights on why guard pages actually were expensive was done in collaboration with Chris, and honestly, some of this was Chris's insights just directly, right? Now, I would like to talk to you about this, but in the interest of time, I'm just going to move on. Just say that guard pages sometimes have costs, and we know how to eliminate these costs. One of the techniques we can use is MPK. And of course, all of this is published. You can read all through the details or talk to me after. Happy to walk through it. And the moment you get rid of guard pages, by the way, makes running things like fast platforms easier because you have to rely on multiple processes less often. And the big thing about avoiding multiple processes is not the overhead, it's the simplicity. One process is just less, workload stealing, less complexity of dealing with multiple processes, pinning, etc. So where does this all leave us? We have improved the overheads, but it's not perfect. So the logical place to go is what does a hardware extension on the CPU for WebAssembly support really look like? Well, you're not going to get a WebAssembly extension in any CPU. You're going to get an isolation extension. You need to be more general. Other CPU vendors tend not to accept it. So we went about trying to design this where we could extension where we could express data and control flow restrictions, interpose on syscalls, which WebAssembly doesn't need, but general code isolation does. And of course, we want to target both WebAssembly isolation and just isolating some binary you found out on the street and you just want to run on your computer now, right? It should work on both. Most importantly, we don't want OS changes because we've seen how long it takes for a hardware feature to get supported in OSs today. Currently, Intel CET, just as an example, 7-8 years before it got the patches into the Linux kernel, which is a tough road to kind of follow. So the key idea in HFI is we're going to talk about regions, which is a lot like segments. We're just given a different name to keep it simple. And we set up our regions, run the WebAssembly code. The WebAssembly code is restricted to the regions, then we exit. And the real trick in making all this work is you need to make the implementation work out for hardware vendors. The naive thing of saying, let's do big 64-bit bounce checks to support every possible use case will not fly, and they've told me as much. So our insight was, well, we need to take advantage of the domain. We need specialized regions. And we have a kind of detailed design walking through all of this and showing how we can actually use very, very small modifications on the CPU to support WebAssembly and eliminate virtually all of the overhead of guard pages, of the base edition, of almost everything. And best part yet, it's also Spectre safe. You at least can't break out of the sandbox if you're using this extension. And so if you kind of put this along the lines of compare it next to the other techniques we have, it really does seem to look pretty good. I do have a little caveat there, which is more for my own sanity. I'm not going to get into it. There is a very, very subtle and complicated way to perform attacks, which requires another solution. It is an open problem. We have an expensive solution, but it's not good enough. Anyway, this extension HFI, co-designed with Intel folks, co-designed with Revos, and also has input from fast companies, mostly courtesy Chris, and also input from the Google Chrome team, courtesy Samuel Gross. And the short version of that screenshot is HFI looks pretty good for Chrome's UberCage custom hand-wrote sandbox for just-in-time compiled code as well, which is kind of a nice touch. So in the last 1 minute, 20 seconds, okay. Let me just tell you this. I'm going to throw something out there very quickly, and maybe I'm wrong. Maybe this is the hot take that's just wrong, but I just want to leave you with something, which is we have a lot of the early adopters of Wasm. So who are the next adopters and why are they concerned? Well, I'm going to actually make the claim that compatibility and security are going rather well, relatively speaking. The part that I'm seeing a bit of a gap is performance, and so this is where we have a lot of work in progress. And one of the big things we're trying to do right now is compare WebAssembly SFI to classic SFI tools. And WebAssembly actually has a lot going for it in terms of control flow, in terms of quick transitions, all of which is formally proved, work with Conrad, and WAW'22. But it also has a bunch of open problems. It cannot eliminate dead reads. We still don't have a great solution for Mem64. And WebAssembly operates on offsets, which means we baked in overheads right at the beginning, which we cannot eliminate. And there's also this other problem of you often have to copy data back and forth, which we have a partial solution to, but it's work in progress. And here's kind of the thing I want to leave with this room. I've tried a bunch of system solutions to the open problems on the last slide. They don't work. The only solution I actually see that's going to work for those problems is now a type-based or small extensions to WebAssembly, which is a pretty good note to end my talk. Please think about this and come talk to me. Happy to take any questions if you have time left.
Thanks so much. We would never know that basically this time yesterday you were just agreeing to fly over and start this talk. So thank you so much again for doing this at short notice. John, would you mind swapping in your laptop right away? And as we do that, we'll take a few questions.
Thank you for the talk. I really enjoyed it. For hardware fault isolation, I saw a bunch of asterisks there in terms of, what, and you also mentioned that you added some caveats. I was wondering if you could speak a little bit more to that. Like, what do you consider to be the risks?
So the asterisks, there were two sets of asterisks. One
Maybe
was
the first one, the first.
Yeah, first one was what does adoption look like? And the truth is, I don't know what Intel has expressed interest to me. Just as it's interesting. I do not know what their expectation on actually building it out is. We'll have to ask someone at Intel. We are working with RISC-V to make this in a TG to actually make this a formal spec. In terms of security, the HFI attack that's possible is not where code inside the sandbox reaches out and touches memory it cannot have access to, but rather it's this complicated attack where outside code can, prime the branch predictors and confuse the code inside to leaking its own data. It's a spectacularly complex attack to pull off, but it is technically there. So which is why I think it's a technical asterisk. I do not know of a single case of a real world attack that has come close to this level of complexity.
So we just have to give it a couple of years.
You'll see a paper about it. I do not know that you'll see a real world attack about it. That's my guess.
I'll ask one quick question then. If there's one feature you could magic into WebAssembly without having to carry out the standards process, what would it be?
Special type. Sorry. One feature that I could magic into WebAssembly spec, a special pointer type, useful for half the things I've talked about.
Okay, thanks so much. One last thanks to Shravan again.